So, let's go through the announcements real quick. Chapter 2, the first chapter 2 homework is due today, tonight. 2.1. The second chapter 2 homework is due in a week on the 12th. The chapter 1 and 2 review for the test on chapters 1 and 2 will also be on the 12th in SI. The chapter 2 quiz will be on Wednesday the 12th. The chapter 1 and 2 exam will be on Monday the 17th. So it's not next week, but the week after. And the chapter 1 quizzes are up here and graded. So you can pick them up after class. Any questions about that? And your grades for the quizzes are up on Blackboard. So, finishing off the chapter, just to make sure I'm in the right place. Yes. Finishing off the last bits of stuff we have for chapter 2. Quick reminder, speed and velocity have different distinct meanings. Speed is a scalar quantity that only has a magnitude, like a car going at 80 kilometers per hour, while velocity is a vector. It has both a magnitude and a direction. A car going 80 kilometers per hour north. And vector quantities can be represented with arrows. The length of the arrow is proportional to the magnitude of the quantity. So you're traveling, if you have 40 kilometers per hour, you draw like an arrow like this. And then for 80 kilometers an hour, you use an arrow pointing in the same direction that's twice as big. For negative 40 kilometers per hour, you use an arrow that's pointing in the opposite direction that's the same size as 40 kilometers per hour. Negative 80, be an arrow the same size as 80 kilometers per hour, but pointing in the opposite direction. So in this image, to the right is positive, to the left is negative. And this is just one dimensional. You can expand to 2 dimensions, but I'm not going to give you any problems where you need to do that in this class. So vectors can be both positive and negative. So this car has a velocity of negative VC. This one has a velocity of positive VC. The walking person has a velocity of VM. These 2 cars are traveling at the same speed, but one is moving in the positive direction and the other is moving in the negative direction. When you add vectors, you can connect them head to tail. And there's a difference between the distance you travel and the displacement. So here is an example where you're connecting vectors head to tail. The distance is 2 meters plus 1 meter plus 2 meters plus 2 meters, which is 7 meters. But the displacement is going to be, you travel 4 meters to the right and 3 meters down. You can draw a triangle that's 4 meters on one side, 2 meters on the other. The third side, using the Pythagorean theorem, you can find that third side will be 5 meters long, because the square root of 4 meters squared plus 3 meters squared is 5 meters. And the direction is southeast, assuming up is north in this diagram. I forgot to clear some stuff. That's not what I want to do. So, one of the the things you can do when you can express things as vectors is talk about relative motion. Relative motion is figuring out how fast what the velocity from a specific point of view is for something. So here, for example, we have a guy on a train. The guy is moving at 1.2 meters per second with respect to the train, and the train is moving at 15 meters per second with respect to the ground. And we want to figure out what speed the guy is moving from the point of view of someone on the ground. So the way you can do that is that the velocity of the passenger with respect to the ground is the velocity of the passenger with respect to the train plus the velocity of the train with respect to the ground. So this is how you can figure out relative velocity. So if we look at this, the velocity of the in the first case, the velocity of the passenger with respect to the ground. Well, we're going to say that this direction is positive again. He's moving at 1.2 meters per second. And the velocity of the train with respect to the ground, that's 15 meters per second. So the velocity of the passenger with respect to the ground is 16.2 meters per second. When they're moving in the same direction, when the medium or the thing that's carrying it is moving in the same direction as the thing that's on it, the velocity is at. But also, they could be moving in opposite directions. The guy could be walking backwards with respect to the train, while the train moves forwards. So here, this is, the A for B, the velocity of the passenger with respect to the ground. The velocity of the passenger with respect to the train is negative 1.2 meters per second plus 15 meters per second, which gives us a final velocity of 13.8 meters per second. So that's 15 minus 1.2. So that's how you can solve these. I can't remember if I put it on the quiz or the test, but there will be a question based on this. So here's an example problem. The general idea is velocity of AC is velocity of AB plus velocity of BC. So velocity of A with respect to C is velocity of A with respect to B plus velocity of B with respect to C. And I like to write it in this order because you can see how sort of the B's hook together, they connect to each other. There's positive direction. And I'll draw a quick picture. We have a boat on a river. We have a river. It's traveling north with a water speed of 15 kilometers per hour. This is velocity of the boat with respect to the water. And the river is flowing south at a speed of 5 kilometers per hour. So a shorter arrow. Velocity of the water with respect to the shore is 5 kilometers per hour. So the water is traveling south at 5 kilometers per hour. The boat has a water speed. The speed it travels in the water is 15 kilometers per hour. So what's the velocity of the boat as seen from the riverbank? We'll call it bank. water. And what would the velocity as seen from the riverbank be if the boat was traveling south instead of north? So there's a quick doodle of that as well. Right. I don't remember what I said. Well, our basic formula is velocity of A with respect to C is velocity of A with respect to B plus velocity of B with respect to C. So the velocity of the boat with respect to the land is going to be the velocity of the boat with respect to the water plus the velocity of the water with respect to the land. So we can plug those in. The velocity of the boat with respect to the water is positive 15 kilometers per hour, because we're going to call north positive, just by convention. And the velocity of the water with respect to the land is minus 5 kilometers per hour. So 15 minus 5 is 10 kilometers per hour. So 10 kilometers per hour north. We could also do it if the boat was traveling south on the water. So this would be minus 15 kilometers per hour plus minus 5 kilometers per hour. And that is minus 20 kilometers per hour, which is 20 kilometers per hour south. negative because it's the opposite direction. And it's faster because now the boat's going with the water. So the water is speeding it up as opposed to opposed to the water, where the water would be slowing it down. You could have the same thing for something in the air. If there's a headwind, that means the wind's coming from in front of the plane or whatever is flying. That's going to slow it down. If you have a tailwind coming from behind, that's going to speed it up. Now, our equation from acceleration is final velocity minus initial velocity over time. We can rearrange this to solve for final velocity. And when we drop an object, we get constant acceleration going down. The distance is 1/2 gt squared. The velocity is proportional to time. So it's going to end up being acceleration times time. When you throw something horizontally, you get a combination of both vertical motion and horizontal motion. So if I throw something like this from one hand to the other, I was better at actually catching things. Probably easier that way. The horizontal, you have straight line motion horizontally and vertical motion, and they act independently. So if you neglect air resistance, a horizontally projected object travels in a horizontal direction with constant velocity while falling vertically due to gravity. So if you fire something horizontally at the same time as you drop something, they will hit the ground at the same time. So here, something thrown horizontally will fall at the same rate as an object that's dropped. And this is why projectiles follow parabolic paths. So just in general, the velocity in the horizontal direction doesn't affect the velocity and acceleration in the vertical direction. They're independent of each other. This leads to some nice effects. The combined horizontal and vertical motion forms a parabola. The horizontal component is always at constant velocity. The vertical component is independent. So if you wanted to figure out how far away something would land if you fired it horizontally, the time it takes to fall, you can figure out from the vertical component, and the distance it travels horizontally, you then figure out from the horizontal component. Now, if you throw something with some upward velocity, it will go up and then down again vertically, and will continue moving sideways at the same velocity the entire time. So here, a thrown football, the horizontal velocity remains constant the entire time, but the vertical velocity changes just like that of an object that's thrown upwards. And that means the speed on the way up is going to be the same as the speed on the way down for each height. But one will be pointed up and one will be pointed down. So if you have a horizontal cannon at the top of a 12.25 meter wall, and you fire a cannonball out of that cannon at 100 meters per second, how much time does it take the cannonball to hit the ground? So remember, when you fire something horizontally, it will fall at the same rate as a dropped object. And because the distance a dropped object falls is 1/2 gt squared, the time will be the square root of 2d over g. That's the vertical distance. So this is just a fall. The calculation is the same as for a falling object. Distance vertically is 1/2 gt squared. So 2 times distance vertically equals gt squared. So 2 times distance vertical over time over g equals time squared. So the time is going to be the square root of 2 times the vertical distance over g. 2 times 12.25 meters over 9.8 meters per second squared is the square root of 2.5 seconds squared, which comes out to 1.58 seconds. And if you wanted to figure out how far it went horizontally, you just take that time, 1.58 seconds, and multiply it by the horizontal velocity, 100 meters per second. So 100 meters per second times 1.58 seconds gives you 158 meters. Okay, hold on. Here, a projectile is fired from the top of a 44.1 meter pole at 5 meters per second horizontally. How long will it take to hit the ground? And how far from the pole is the projectile when it hits the ground? Problem has 2 parts. First part, how long it takes to hit the ground. Same as the last one. The distance fallen is 1/2 gt squared. The time is square root of 2 times the distance fallen over g. So that distance is 44.1 meters. So 2 times 44.1 meters over 9.8 gives you 9 seconds squared. Time is 3 seconds. It takes 3 seconds for this for this projectile to hit the ground. For part B, how far from the pole it is, well, now we know what the time is. The distance traveled horizontally is velocity in the x direction times time. So 5 meters per second times 3 seconds or 15 meters. So this will land at the bottom of the pole, 15 meters away from the pole. Now, if you have no air resistance, you get some nice things. If there's no air resistance, projectiles will follow a parabolic path. They'll be symmetric. They'll be the same on both sides. And you'll get your maximum range, your maximum distance at 45 degrees. So if you're firing a projectile at some speed, the angle that will give you the maximum distance if there's no air resistance is 45 degrees. And the formula to figure out the range of a projectile on an even surface not that you'll actually need this, but the range formula is, well, I think I have it written on the slide, because I haven't perfectly memorized it. Yeah. V initial squared over G times the sine of 2 times the angle. You're not going to actually need to use this formula. It's just an example. But because of that, this maxes out when the angle is 45 degrees, because sine is maximum at 90 degrees, and you're doing the sine of twice the angle. Another aspect of this is that two projectiles fired at angles that add up with the same speed at angles that add up to 90 degrees. So two projectiles fired with the same speed at complementary angles, that's angles that add up to 90 degrees, will travel the same distance horizontally. So if V1 equals V2, and theta 1 plus theta 2 equals 90 degrees, range 1 will equal range 2. Basically, here is an example. If you fired at 60 degrees and at 30 degrees, they'll travel the same distance horizontally. The 60-degree one will travel more slowly horizontally, but it'll take more time because it goes higher. The 30-degree one will travel faster horizontally, but it'll take less time because it goes lower. And those factors will even out if the two angles add up to 90 degrees. And this is actually a fallout of this formula. It turns out if you take two angles that add up to 90 degrees, sine 2 theta will be the same for both. Now, under real world conditions, air resistance messes with this. And your paths are not symmetric. And so it actually, the optimal path is at a little bit lower angle. In general, the lower angle is going to get of a pair of complementary angles would give you the better distance because you spend less time in the air being slowed down. But figuring out exactly where things are going to add with air resistance is really quite complicated, because drag from air resistance is not simple. It depends on how fast you're moving and other things. So it varies through the path, and it's just very complex. So here are some of the things that you need to consider with a projectile, like in athletics. The angle that you release it at. Spin on the ball can affect this, because spin can add lift, which can make you fall more slowly. The size and shape of the projectile, the speed of the wind and the direction of the wind, those are going to cause the object to move, because the wind will apply a force. The weather conditions, humidity, rain, snow, etc. The altitude of the field. So if you're, say, playing baseball here in Chicago or playing baseball in Denver, your ball is likely to travel further and travel faster because there is less air. Why there's lots of home runs in Denver. And there's an additional advantage there that if you train in less air, you adapt your body for less air. So when you go somewhere with more air, you have more oxygen available to you. That also is an advantage. But that's a different sort of advantage. And then the initial horizontal velocity. In order to make it out of the park, for example, before gravity brings it down, a baseball has to leave the bat at some high speed. It needs to be moving fast enough. And what the required speed is based on all these other factors. So here's an example problem where we're going to ignore air resistance. If I fire a 55 kilogram cannonball at 34 meters per second at an angle of 25 degrees above the horizontal, and then I fire a 20-gram paintball at 34 meters per second at some angle that is greater than 45 degrees, and it hits the cannonball. Neglecting air resistance, what angle did I fire the paintball at? And which of those took longer in time to reach its destination? And I will tell you, there is some unnecessary information in this problem. I gave you more information than you need. Doesn't cause any contradictions or anything, but some of the information is unnecessary. I'll give you a few minutes to think about this. So the unnecessary information is the masses of the balls. Don't need that. What you know is you have two projectiles that are at two different angles and are reaching the same place with the same starting speed. That means the angles need to be complementary. So the two angles, theta 1 and theta 2, have to add to 90 degrees. Theta 1 is 25 degrees. So theta 1 plus theta 2 equals 90 degrees. So theta 2 is 90 degrees minus theta 1. 90 degrees minus 25 degrees is 65. So 65 degrees is going to be the angle of the paintball. And the paintball is on the higher path. It's traveling a longer path. It's going to take more time. It's actually also going, not only is it traveling a larger distance, it actually will also be traveling on average slower than the cannonball at the lower angle. So the paintball will take more time to travel that distance. But the masses are irrelevant. So that's the end of the chapter. So here are some important equations. Velocity, average speed is distance over time. Also, average velocity is displacement over time. Distance is the distance traveled starting from rest is 1/2 acceleration times time squared. For a dropped object, distance traveled is 1/2 g times time squared, where g is 9.80 meters per second squared, or 32 feet per second squared. That's the acceleration of gravity. Acceleration is change in velocity over time, or final velocity minus initial velocity over time. Final velocity is initial velocity plus acceleration times time. Centripetal acceleration is the speed you're traveling around the circle squared, divided by the radius of the circle. And for relative motion, velocity of A with respect to C is velocity of A with respect to B plus velocity of B with respect to C. Those are the important equations for the chapter. That is it for today. So we finished chapter up. Again, your first homework is due tonight. Your second homework is due next week, which is also when you'll have the quiz. And we'll have our first test on chapters 1 and 2 Monday of the week after that. And you can pick up your graded chapter 1 quizzes here. They're in alphabetical order. From when I was entering the grades.